Hello, I'm Spencer, and I'm going to be giving a presentation on a generalization of probability that is mainly used in quantum mechanics. We will start out by reviewing classical probability, and then we will go over the new formulation, and then at the very end, we're going to show how that formulation is used in quantum mechanics. There will be a pretty steep learning curve, or a pretty steep difficulty curve when we get to the quantum mechanics bit, but I believe in you guys. So, in classical probability, we start out with the notion of a universal set, the universal set U, and we will represent events as being subsets of that universal set. So, for example, in the case we have a dice with 6 sides, then our universal set would be some denumeration of all the 6 sides. And then we could have our probability function we define our probabilities so that they sum to 1, and each element has an associated probability. So we could choose many different probability functions. Maybe we have them all equal, or we could have a weighted dice. But the important thing is that it's based on a set, and that the subsets of this can have associated probabilities, and they represent the events. And the probability functions classically must obey 3 axioms. The first is that the probability of the universal set needs to be 1. The second is probabilities are non-negative, and these are mostly just formalities to make things nice. And the third is that this concept of being mutually exclusive. So 2 sets would be mutually exclusive if their intersection is empty. And if that's true, then the probability of the union is the sum of the individual probabilities. So it lets us split up probabilities in different things. But we've seen this before, and we should be fairly familiar with this kind of thing. So to motivate why we need a generalization, we're going to observe the 2-slit experiment, which is a famous experiment in physics. So the experiment is that you shine light at a screen with 2 very small holes in it. We'll call them slits. And you get this interesting interference pattern. So we will have A represent the event that the particle goes through the first slit. B will be the event that it goes through the second slit. And C is a little bit different. C represents the distribution of where it is found. So C is the event that the particle is found at a certain position on the screen. So to make that a little more clear, so this is represented vertically, but now it's represented horizontally. There's a slight flipping of the axes. So this A intersect C is, again, the event that it goes through the first slit and it is found at a certain position. That is represented by this curve. So slit A would be around here, around the center of the normal distribution. And B intersect C is similarly another normal distribution centered at where slit B is found. So this first curve would be if B was covered and the particles could only go through A, and the second similarly is what A would be covered, they can only go through B, and they're found at position on the screen. So now we considered that it can go through either slit. So this is the probability that it goes through slit A or it goes through slit B, and then it is found at a certain position. By De Morgan's laws, we can expand this into its 2 components that we observed earlier, that it goes through A and it's found at position, and it goes through B and it's found at a position. So this is a copy of the previous slide, the 2 individual cases where one of the slits is covered. So if we look at this, we just union the two individual bits. So we would end up with a distribution that is two-humped sum of two normal distributions centered at, so it's A and B. But surprisingly, that's not what we see when we do experiments. When we do experiments, we get this interesting interference pattern where there's peaks and troughs, and it's not just a simple sum of two distributions, two normal distributions, like we would expect classically. And this is the fundamental problem with classical probability. And it's this idea that things can distribute. So because the events are represented as sets, then we have lots of things that come from set theory, such as distributivity, that are baked into the structure of the probability that we formulate on top of it. And in this specific case, this distributivity over intersections and unions breaks when we do experiments in real life. So we want to get away from representing events as sets to generalize into more powerful theories. So the first step in doing that is the concept of a partially ordered set. A partially ordered set is a set with a relation, and the relation has three properties. It's reflexive. Every element is less than or equal to itself. And if A is less than or equal to B, B is less than or equal to A, then A equals B. And the third is transitivity. If A is less than B, B is less than C, then we have that A is less than or equal to C. Very intuitive properties that we define for our partial ordering. So these events in the set will ultimately take the role of, these elements in the set will take role of events. That's going to be their interpretation. So instead of having the events being sets, we have events being elements, but we're going to want to get into more structure before we get too far into the interpretation. A quick example of a partially ordered set to hopefully break this, our usual understanding of what less than or equal to means. We take our partially ordered set to be the natural numbers, and we could define A less than or equal to B if A divides B. It's important to check that our definition for less than or equal to follows the three axioms that we went over on a previous slide. So some examples. 5 would be less than or equal to 10 because 5 divides 10. Similarly, 2 is less than or equal to 16. But 2 would not be less than or equal to 15 because 2 does not divide 15. And 3 does not divide 4, so 3 is not less than or equal to 4. So the two main concepts we want to get out of this is that to break our standard understanding of less than or equal to a more abstract thing. And notice that sometimes elements can't be compared. So we could have two elements that it doesn't necessarily make sense to say that one is less than or equal to the other. So in this case, 2 is not less than 15, and 15 is obviously not divide 2. So this is an important thing we're going to have to deal with in our theory. So on top of our partially ordered sets, so we have an ordering, we want to define two binary operations that go from the set to itself. And here's the definitions. The V shape is going to be is going to be thought of as or, and the upside down V is going to be thought of as and. I remember that because you can imagine drawing a little bar and then it looks like an A. So the definition of A or B is essentially going to be the supremum. So A or B is going to be greater than or equal to the components individually. And if we have another thing that's greater than the components individually, then we have that A or B is going to be less than the thing that's an upper bound. This is essentially the same definition as an infimum, as a supremum, that you'd see in analysis. Similarly, if the object A and B is going to be a member in the partially ordered set, such that it's less than or equal to the individual components. And if there's another thing that's less than or equal to the individual components, it is smaller than our object. So it is the smallest, it's the greatest lower bound, or the infimum, of our structure. So just as we saw before, two elements may not have a meaning of less than or equal to. So similarly, our binary operations may not be defined between all elements. So the or and the and may not exist. So it doesn't, so we got to be careful when we write this, basically. We got to be careful that it exists because it may not. So this is a very big problem because we want to be able to have a meaningful comparison between events if we want to have our probability be useful at all. So the way we get around that is define it away. So we define a lattice as to be a partially ordered set with the and or operations defined between all elements. So now we define away all the ambiguity and the problems of ill-definedness, and we call this structure a lattice. So two important concepts from a lattice are the concept of a minimal and a maximal element, which I'll denote like this. The minimal element is less than or equal to all things, and similarly the maximal element is greater than all elements in the lattice. So it's important to note that these may not exist, but if we take all the elements in the lattice, we can essentially intersect all of them to define the maximal element, and or intersect or all of the elements to find the minimal element, and we'll and all of the elements to get the maximal element. And we can define these minimal and maximal elements on top of the set if there's not already ones that exist in the partial ordering. So the last important definition we have for a lattice is the not function. It needs to be a bijection. So for each element in the lattice, the not takes it to another element in the lattice. And it has these three properties. Not of A is equal to A. A and not A is the minimal element. If A is less than or equal to B, then not B is less than or equal to not A. Again, I think these are fairly intuitive based on our standard understanding of what not and less than or equal to means. But it's important to see some examples to abstract that away. So we can steal the example we used earlier. So the set will be the natural numbers with the partial ordering of divisibility. In this case, we have that the or between two elements is the least common multiple. So this or is again going to be the smallest element that both A and B divide, which is the least common multiple. And similarly, the and between two elements is going to be the greatest element in the natural numbers that divide both A and B, the greatest common divisor. So already this is fairly interesting to see that we can represent concepts we're very familiar with, like least common multiple and greatest common divisor, with this structure that we've created. And there's very elegant formulas sometimes that result in the structure of the lattices. So another one, obviously we could have the real numbers with the standard ordering. The or between two elements is going to be the maximum of the two elements. The and is going to be the minimum of the two elements. And note that neither of these have an obvious not function. And that comes from this property that the and between an element and its negation is 0. And we need to have a bijection. So for instance, in this case, we'd want our minimal element is 1. And we'd want, like for example, 2. We'd want another number that such that the greatest common divisor between 2 and that number is the minimal element is 1. And because the greatest common divisor of 2 and like it'd have to be a prime, it'd be 2 and 3. The greatest common divisor is 1, but then not of 3 would have to be 2. And it's not super clear how we would define that for composite numbers. And similarly, in the minimal element for the real numbers would be negative infinity if we append negative and positive infinity to this lattice. And it's not clear the min between 2 and what is negative infinity. Well, you need negative infinity, but then negative infinity is used up because we can only compare negative infinity to one other thing. So neither of these have a good not function that we can define on them. So the third example of a lattice is going to be the power set of a function, the power set of a set. And the concept of less than or equal to is going to be subset. And this is actually exactly the same as classical probability. So this shows that this really is a generalization, and we can still represent classical probability in this more generalized sense. And here we see how nice the notation is. The or between two sets is going to be the union. The and is going to be the intersection. Very nice comparison between the notation. I really like this notation. And the not is just going to be the complement with the universal set. And again, this is just the special case of classical probability, now represented in our more general setting. So the last concept we need is a probability function on our lattice. So the probability function goes from the lattice to 0, 1. There's some assumptions baked into here. So the probability of the minimal element is 0. If A is less than or equal to B, probability of A is less than or equal to the probability of B. And this interesting property, A is less than or equal to not B. If we have that, then the probability of the or of two elements is the sum of their individual probabilities. So this is very similar to something we saw in the classical case. So the probability of the union would be the sum. So here we had the intersection of two elements being the empty set. Now we have this property. So this is going to be our new understanding of what mutually exclusive means. And the reason is because if you assume this, you can show that the and between the two elements is the minimal element. So this is a more general idea that is stronger than our definition that we use in classical probability. And it also is not clear that this is reflexive, but you can show that if A is less than or equal to not B, then that implies that B is less than or equal to not A. So it is a reflexive condition for mutually exclusive. So now we've developed our lattice, and we can change the structure of the probability by changing what lattice we use. And we have a lot more flexibility now because it's not necessary that that these and or operations are going to distribute over each other like they do in the classical probability. So this is the structure of our lattices. Next, we will go over the quanta formulation. And I'm going to skip over a lot of the underlying linear algebra and analysis. I'm going to try to explain it in a way that both the people that are knowledgeable about the topic learn something and the people that are unfamiliar will also learn something. So the lattice we used is going to be based on linear operators in a Hilbert space. And think of these as just 2 by 2 complex matrices. And these 2 by 2 complex matrices will have this property that they will be such that p squared equals p star. This is the adjoint, which is equal to the conjugate transpose of the matrix. And these three conditions, these equalities, are known as P being an ortho projection. And there's lots of structure associated with this that make it useful for this context. And the partial ordering between elements is going to be A is less than or equal to B if B minus A is positive semi-definite. And this is my favorite definition of positive semi-definite. For those in the know, the determinant would be greater than or equal to 0. It's including equality. It's not strictly. And this notation saying this is kind of annoying, so we will use a notation that P greater than or equal to 0 denotes that P is positive semi-definite. And this is definitely an abusive notation, but it's very nice notation to use, because if we say that B minus A is positive definite, that means it's greater than or equal to 0. And you can imagine rearranging that. That means B is greater than or equal to A. And that's the same thing as our standard definition. And this is a very surprising property that works. It's not clear that this is a partial ordering on the sets. It's not clear that these are even closed under that premise. But it turns out they are, which is really cool. So our definitions of ands and ors is going to be as follows. If we have P and Q in our set, P and Q is going to be the ortho projection such that the image of the new ortho projection is equal to the intersection of the two images. Again, we see the useful notation transferring over. And the or between two elements is going to be the ortho projection such that the image of the new ortho projection is equal to the direct sum of the images of the two subspaces, or the two spaces. Again, this is the all possible sums of elements in the image of Q plus elements in the image of P. It's not just the sum of the two spaces. And there's also a very nice formula for the negation. The negation of an ortho projection that is just going to be the identity minus the ortho projection. Again, incredibly surprising that this satisfies all of the notions of not that we defined earlier, but it turns out that it does. And for the special case of commutativity between the ortho projections, we get really nice formulas. For the and between two elements is just the product, and the or between two elements is the sum minus the product. Very nice formulas that result from this very high level math. So what we haven't done yet is define a probability function on these on this structure. So the probability functions are going to be denoted by this operator. And the operator is going to live in the same space that the elements in the lattice do. It's going to be in the linear operators on a Hilbert space, such that the A is positive semi-definite, and the trace of A is 1. Many things surprising about this. Mainly that the probability functions are going to live in the same exact space that the elements in the lattice are. And another interesting thing is the trace of rho is going to be 1. it's not clear that the trace, it's not clear why we see the trace here. But it turns out the trace is actually independent of the basis, and it's equivalent to the sum of the eigenvalues, so it is a very important aspect of an operator. And this results in a very, very, very nice formula that the probability of a given operator is equal to the trace of rho times q. And again, we see trace. And again, we see the usefulness of the probability functions being essentially isomorphic to the subset of the space, the same space that the lattice is in, because we can just take a product. Very, very nice and elegant formulation. So I want to go over some quick surprising facts before we end about this information. So we went over briefly what the operators would look like if they commute. If we restrict this space to the commutative operators, the operators that commute, then we essentially get a probability structure that's identical to classical probability. And we could change basis so that the density operator is diagonal, and the diagonal elements of the density operator are going to essentially be the probabilities of the diagonal elements of Q occurring. So it's really interesting that we can essentially use traces to represent classical probability instead of what we learned as sets and intersections and unions between them. So the measurements of a system are important for quantum mechanics. There's certain things that happen, and it changes how the probabilities are observed. But the measurements of the system are also represented as linear operators in the same Hilbert space. So the measurements are in the same space as the probability functions are in the same space as the elements in the lattice. So it ends up being a very, very elegant way of combining probabilities and measurements and elements into a very concise formula oftentimes. Of course, the formulas can get very complicated if you look hard enough. Again, in quantum information theory, the elements, the orthoprojections, are called qubits. And in certain settings, you can encode more information in 2 qubits than 2 bits, 2 classical bits of information. So, like that's obviously very useful. That's why we're working so hard at quantum computers, because we can formulate problems quantum mechanically such that it's much better and much more efficient at solving them than classically. So this is just one possible formulation of our generalized notion of probability. There's theoretically other probabilistic formulations that could contain more information per bit than quantum probability. And that's also very surprising. It's interesting thinking about what out there. Like, we have stuff out there that might be better than what we are using, than what we even know. So that's an interesting area of research that I'd like to learn more about. But anyways, that concludes my presentation. Don't hesitate to reach out if you have any questions. And thanks for watching.